Thank you for inviting me here. It is a pleasure. So yes, I'm Andrey. I've just finished my PhD at Cambridge. And yeah, so I'll be giving a talk on how do you estimate uncertainty in in supervised learning for discriminative models. So a lot of this is joint work with my professor, Mark Gales, and an undergrad intern, Bruno Mlodozenic, so kudos to them as well. So anyways, what is our scenario? Our scenario is, for uncertainty estimations, we have some kind of model, and we have some test input X. And for this input, we would like to obtain a prediction. So, obviously you want to use the model for something. But in addition to your prediction, we would also like the model to give us some measure of uncertainty or confidence in the prediction it's making, so we can then do something about that. For example, we'd like to accept the prediction, or maybe reject the prediction, or use it for some end task to make AI safer. So here's an example of a model like this for regression. This is a Gaussian process. It's a non-parametric Bayesian model. It's a distribution over functions. It predicts a mean and variance, and the mean is a prediction, obviously, and the variance is a measure of uncertainty. And it has a nice property that the variance increases the further out you go from the region where you have training data. So as we go further away, the variance gets bigger. This is a nice property, and we want this. So how do you do this for parametric models, for classification models? Basically, we'll be talking about this. Now, I will stress this multiple times, but I have a very strong belief that uncertainty should be considered within the context of applications. For example, you'd like to do threshold-based outlier detection, like misclassification detection, out-of-distribution input detection, or to detect maybe adversarial attacks. Or you would like to use it for active learning, collect some more data based on measures of uncertainty, or maybe you'd like to do exploration in reinforcement learning driven by your measures of uncertainty, or maybe something else. Doesn't matter. So there's many things you could use uncertainty for, which is why we care about it. So the talk is structured into generally 5 sections. First, I'll discuss where does the uncertainty in our predictions even come from. Then I'll discuss ensemble approaches, or Bayesian approaches if you like. They're related. Then I'll discuss some of my work, which is prior networks. Then I will compare the two, and in addition, there discuss how do you actually assess the quality of uncertainty. And finally, I'll sort of show a bit of our work in progress, which is interesting in that it combines the two, or tries to combine the two approaches even more than prior networks usually do. So, uncertainty in predictions. Let's go from there. Oh, by the way, if any of you have any questions, like you misunderstood something or didn't hear something clearly, ask right away. But if you have like conceptual debate-style questions, can you wait till the end? Cool. So in general, we have sort of 2 classes of sources of uncertainty. You have data uncertainty on the right, on the left, and this is when you have like classes overlapping. And then you have things like our inputs are far away from the training data, and that can be due to data sparsity, the case in the middle, or because our input is really, really far away and it comes from an entirely different distribution than our in-domain training data. And both of the second and the third are generally considered epistemic uncertainty in Bayesian models, but I will only refer to the last one, and I'll call it knowledge uncertainty. So in this case, in this talk, we refer to knowledge uncertainty. It's only the last scenario. And in fact, they're related, but I think it's easier to conceptualize the last one. So, but we'll start with talking about data uncertainty, also known as aleatoric uncertainty. And here, you have a simple distribution. You have 3 classes. The classes are not overlapping. The blue lines indicate the decision boundaries, or the entropy of the decision boundaries. We have a green input here. And it's easy to assign this input to a class, probably class 2 here. And basically, there's very little uncertainty in this situation. But now consider this, what happens when the classes start overlapping. The classes overlap, and now it's far harder to attribute this input point to a particular class. We don't know whether it's class 1, 2, or 3 because they're overlapping, and the feature there has properties of all classes. This is considered data uncertainty. It's data uncertainty due to class overlap. So yeah. To conceptualize using like actual figures, here consider the digits 1, 2, and 7. Here they're distinct. You can easily tell apart which one is a 1, which one's a 2, and which one's a 7. And now we have a situation when they're sort of similar to each other. They're written in such a way that it's maybe not obvious which one's a 1, 2, and 7. They're still distinct, but not as much. This is a concrete example of data uncertainty for classification tasks. So in general, data uncertainty is a known unknown. You have data the training data tells you that in these certain regions, the classes are overlapping. So you know that in these cases, you can't confidently make any predictions. Now, in regression, which I don't really consider in this talk, but in general, data uncertainty takes the form of homoscedastic or heteroscedastic, which means input independent or input dependent noise. So yeah. Let's consider data uncertainty a little more mathematically. So this is entropy, so this is your predictive distribution here. This is your predictive posterior for some test input x star, and basically we consider the entropy of that. And that is your true predictive distribution. This is the thing which generated the data. There's no model here yet. This is the true underlying conditional distribution of the data. And the entropy of that is your estimate, is the true estimate of data uncertainty at that point. Now, obviously we'll have then some particular model parameterized by parameters theta hat, and the entropy of that posterior, predictive posterior, will be an estimate of data uncertainty. And because if you have a model trained using standard maximum likelihood, which is equivalent to minimizing the KL divergence between the model and the true underlying data distribution, the more data you have, if you have the correct model class, in the limit, your model trained with maximum likelihood will capture data uncertainty in its predictive posterior. That's nice. We sort of get it for free, assuming we're not overfitting crazily to some data set. So that's nice. And just a reminder, this is a low entropy distribution, this is a high entropy distribution, just in case. Right, so we've talked about data uncertainty. Now we'll, yes? I'm about to go to there. Don't worry, patience. Right, so now, so now we'll be talking about knowledge uncertainty, right? So we've discussed data uncertainty, and now we're talking about knowledge uncertainty. So here we have some input. It's really far away from the training data, and based on this training data, we don't really understand that input. You know, this could be a new class, an old class, maybe the entire input space wraps around itself in some really weird and complex way. We have no idea. We literally do not know, which is why it's called knowledge uncertainty. Here's a more concrete example. We have, on the top left, we have MNIST digits. This is a data set of handwritten digits 0 to 9. And on the top right, we have the omniglot data set, which is a bunch of handwritten characters from different alphabets. If a model is trained on MNIST, there's nothing there which tells it about handwritten digits from multiple different alphabets. So we don't know those classes. We don't understand that data. So it's basically an example of distributional mismatch, data set shift, knowledge uncertainty. But we can have a less extreme version. Consider the fact that, for example, consider the situation when we have, in our training data, only the digits 1 and 7. You only see a 1 and 7 with the 1 with no hat and a 7 with no crossbar. And you only see 1s like that and 7s like that in your training data. But suddenly in your test data, you do have a 1 with a little hat on the top and a 7 with a crossbar. And this is another form of data mismatch, but maybe it's less extreme. Maybe your model will generalize, maybe not, but it should be a little more uncertain due to knowledge uncertainty for these inputs. So in general, we've had data uncertainty, it's a known unknown. Knowledge uncertainty is an unknown unknown. You don't know anything about that region, subject to maybe assumptions you've built into the model. But you don't know anything about that region, it comes from somewhere else, you don't really know anything about it. So you have no knowledge, and it's an unknown unknown. You literally can't know anything about it. Now, the reason we care about separating out the sources of uncertainty is because the actions one wishes to take in some context may depend. For example, in active learning, you don't want to collect data from regions of high data uncertainty, but you do want to collect data from regions you don't know anything about, because that's useful. And separating out the two sources of uncertainty is what ensemble approaches, which I'll discuss next, are very good at. They're the theoretically correct way of going on about it. And there we'll discuss how to actually estimate your knowledge uncertainty or your model uncertainty. So we've discussed sources quickly. There's not much to it. Now we'll switch to ensemble approaches, which one can call Bayesian approaches as well, but I prefer to keep it more general than that. So I'm sure you've all seen this over the entire week. Bayes rule. You get your posterior over model parameters given the data by picking up prior and getting some data, and yeah, you do Bayes rule. You've seen this all week. You've also seen this all week. This is your Bayesian inference. In theory, you can take your model parameters, you can integrate them out, and obtain a Bayesian predictive posterior or an ensemble predictive posterior. Standard stuff. But we can also consider sampling an ensemble of models from your posterior and not integrating them out. We can also consider maintaining multiple or M different models, and we can consider how the behavior of that ensemble. And the behavior of that ensemble will also be very much controlled by your choice of prior, whether it's implicit or explicit or whatever else. Anyways, so let's consider how uncertainty factors into all of this. So let's consider the predictive posterior, and let's consider the entropy of the predictive posterior. Standard stuff, so you just take the entropy of the thing, and if you have an ensemble, you'll basically do a Monte Carlo approximation to it. You can you can take the average of all your ensemble predictions. Standard stuff. You take the entropy of that, and that becomes a measure of total uncertainty. It is now not just data uncertainty, it is also knowledge uncertainty, which comes from the fact you have uncertainty in your model parameters, or in the model itself. Now let's consider the ensemble again. You have the ensemble of models. Each of the models in your ensemble captures a slightly different estimate of data uncertainty. So here we're talking about a single model within an ensemble, and each of them only captures data uncertainty. But together, the ensemble will capture knowledge uncertainty as well. So here we can obtain an ensemble estimate of data uncertainty by considering the average entropy of each model in the ensemble. So previously, we considered the entropy of the average. Here, we're considering the average entropy. And this is a measure of expected data uncertainty, taking into account your model uncertainty. This is not always the same as the entropy of the predictive posterior. And when it is and isn't the same is important for estimating knowledge uncertainty, as you'll see later. So, or model uncertainty. Here we're talking about model uncertainty, and I'll say how it relates to knowledge uncertainty a bit later. So consider a situation where your ensemble is consistent. Each of the models in your ensemble are giving the same prediction. Obviously, in this case, the entropy of the average is the same as the entropy of each model in the ensemble, therefore the same as the average entropy, and the difference of the two is 0. Now consider the situation if your ensemble are diverse. So each model in your ensemble is very different to all other models. So in expectation, when you average it together, your total uncertainty will be very high. The entropy of the predictive posterior will be very high. But the average entropy of each model in the ensemble might be much lower. And therefore, this difference will be bigger than 0. In general, this difference is always greater than or equal to 0. So the difference of the two is your model uncertainty. When your ensemble is making a bunch of diverse predictions, means that each of the models don't really know what they're doing. For example, consider the situation where you get a bunch of economists in the same room, and you ask them a really simple economical question, and they all sort of give you the same answer, and they all agree. And it's fine. And then you get a bunch of, then you ask them a question of when will the next, what's the price of Bitcoin tomorrow? And they all suddenly disagree, because none of them knows it. And this is exactly the same case. When you have multiple experts and they all disagree, it means they're asked a question which they don't understand, knowledge uncertainty. Now let's consider this expression, this difference of the entropy of the expected and the expected entropy. This is in fact mathematically equal to the Kale divergence between the joint distribution over your prediction y and the model parameters theta, conditional on the test input x and your training data, and the factored out marginal distributions. This is mutual information. It is a measure of independence between the random variables, y, the prediction, and the model parameter. And basically, it's asking the question is, can we figure out which model which made which prediction? Can we figure out that model 35 made prediction 35? And if we can determine y given a knowledge of the parameters, and vice versa, that means that each model is making a unique prediction, and they're diverse. But if all the models are the same, then it's impossible to know which model actually made the prediction, because they're all the same, right? So therefore, mutual information between y and theta is in fact this difference of the entropy of the expected and the expected entropy, and it is a measure of model uncertainty. Now, so model uncertainty does capture knowledge uncertainty. So Bayesian model uncertainty, or epistemic uncertainty as it's also called, should capture knowledge uncertainty. However, this is conditional on the fact that you have an appropriate prior. Just like in a Gaussian process, if your variance will increase the further you go from the training data, assuming you've chosen the right kernel. If you haven't, it's not going to necessarily increase. Same thing here. If you've chosen the right prior and model architecture. Now, math is nice, but pictures, yes, sure. Sorry? Right. P capital is over discrete random variables, and P small is over continuous random variables. And I think I've been consistent, but maybe not always. Right, so yes, math is nice, but pictures are better. This is basically an illustration of what I've been talking about. You've got your prior, you've got your training data, you get a posterior of one parameters, you sample n models. I really, didn't have time to change the indexing on the things, but they should be going from 1 to m, not n, but never mind that. So you have m models here, and here they're all agreeing. They're all agreeing on class 1, they're all giving the same prediction, and the predicted posterior is also the same. Here, there is no answer, here the prediction is very certain in class 1. It's all fine. Now imagine here where each of the models, the ensemble is still consistent, but now each of the models gives you a very high entropy posterior. That means there's a high degree of data uncertainty, but because all the models are agreeing, the knowledge uncertainty is small. In fact, it's 0, right here. And now, your knowledge uncertainty is high. Each of the models is giving you a very different prediction. The predicted posterior is very high entropy, but the average entropy of each model in the ensemble is not necessarily high entropy. And this is this is basically when your mutual information will be non-zero. So yeah, everything clear? Cool. Any questions at this point? Excellent. Now, this is all nice. This is the theoretically motivated way of doing knowledge or epistemic uncertainty. This is very Bayesian and very cool. But, and ideally you'd like to calculate all these measures of uncertainty, both the entropy of the predicted posterior, the entropy of the predicted posterior, the expected entropy of the predicted, the expected entropy of each model. You'd like to obtain closed form solutions and just compute it. But, as I'm sure you've all been told this week, inference is intractable for neural networks. Also, Bayes' rule is also intractable for neural networks in the general case. So you have a problem. So what can we actually do? And well, you can use approximate inference. You can maybe compute some approximate posterior of a model parameters Q. You can then use variational approximations for the measures of uncertainty, or you can consider Monte Carlo sampling-based approximations is what we do here in general. And there's a whole world of different approximations. There's very many, lots of work. This is a very small list, but for example, for variational inference, you've got like Bayes by backprop, probabilistic backpropagation, amongst many other things. For Monte Carlo style methods, for Bayesian Monte Carlo style methods, you have Monte Carlo dropout, which some might or might not say is Bayesian, depending on who you ask. You have stochastic gradient Langevin dynamics, you've got the fast unsampling via mode connectivity, you've got stochastic weighted averaging Gaussian, many things. But you can also consider non-Bayesian ensembles, and they have similar properties. You can consider ensembles constructed via Bootstrap, which is applied to deep Q networks by DeepMind. You can also consider deep ensembles. Basically, you randomly initialize a bunch of different models, and you train each of them separately to convergence, and then you have your ensemble. In this work, I'll be doing experiments using deep ensembles, simply because it's actually pretty good, while being theoretically super, super, super simple. So if in any experiments where I talk about ensemble approaches, and quote any numbers for ensemble approaches, it's that. Cool. Now, the issue is that it's in practice, while theoretically it's all nice, in practice it's hard to guarantee the diversity for out-of-domain inputs. The diversity of the ensemble will depend very much upon your explicit or implicit selection of prior, the nature of the approximations you make, the architecture of the network, the properties inside of the training data. And ensembles may also be computationally expensive. I mean, there's been a lot of work over the past few years making approximate inference much more scalable, and it's really getting there. There's even some nice results on ImageNet, but it's still more expensive than training just a single neural net. So, yeah. So we've come to the end of the ensemble bit, and here I'll talk a bit more about my work and how I try to overcome the issues inherent in ensembles. So, hands up who knows what a simplex is? Hands up, anyone? One person, two people. Okay, a simplex, okay, very simply, a simplex. Very simply, a simplex is a space on which categorical sum-to-one discrete distributions exist. Any, like for example, 3-class, in this case, discrete distribution will be a point on the simplex, and each point on the simplex is associated with some level of uncertainty over discrete classes. For example, if you're in the center of the simplex, that means there's very high uncertainty. You've got flat distributions. If you're at the corners, you're quite certain. Right. And now you can visualize your ensemble as a bunch of points on the simplex. For the same input, Each of the different models is making predictions. They all predict a distribution over class labels. So you can plot that as a bunch of points on a simplex. And you can visualize the three behaviors of confident at a particular class, consistent but data uncertainty at the center, and knowledge uncertainty where your predictions are all over the simplex. Basically, this is what happens. So you can visualize it that way as well. Now, here I drop the very important concept, is a distribution over distributions. An ensemble is a bunch of samples from a distribution over distributions. You can think of sampling model parameters from an ensemble, and given that set of model parameters and a particular input, you will have a distribution over output distributions, which you can then plot as a bunch of points on a simplex. This is equivalent to considering explicitly a distribution over output distributions mu conditional on your input and your training data, where mu is basically the probabilities of all the classes, and each mu m is a particular point on a simplex, right? So again, these are your samples, and this is the distribution from what it's sampled from. You're confident here, your data uncertain here, and your knowledge uncertain here. Yes? Sorry, I quite... Right, what I meant here is that when you construct an ensemble, it is equivalent to thinking there's some implicit distribution over, sorry, I'm using the word implicit in the sense that you haven't explicitly specified a distribution over outputs. It's not in any way, I don't think it's related to implicit or non-implicit inference, which you did yesterday. But yeah, anyway, so there's some implied underlying distribution over outputs which your ensemble represents. And this is that distribution. So when you have a bunch of predictions or like output distributions mu for a particular input m, they can be seen as sampled from this distribution on the right. When you're confident, where you're data uncertain, and when you're knowledge uncertain. Basically, this is the same thing. I also saw a question somewhere on the left. Was that answered? Okay, cool. Right. Yeah, so when I use the words implicit or explicit, I don't believe it has anything to do with what you did yesterday with semi-implicit something models. Anyways. Now here, explicit. So what I propose to do is to explicitly parameterize this distribution of output distributions using a neural network, which I call the prior network, although it really should have been called the posterior network, but I thought prior sounded cooler at the time. Anyways, so we're going to approximate this distribution of output distributions with a particular set of model parameters, theta hat. So we are no longer Bayesian because we no longer maintain a distribution over model parameters, but we are trying to emulate the distribution over output distributions, which a distribution over model parameters induces. You can also obtain the predicted posterior here, equivalent in the same way by integrating out the mu's. So it operates in a very similar sense like the ensembles. But now we have a model on the output of which we have a distribution of output distributions in a very explicit form. And again, the goal is to construct this model such that it emulates the behavior of an ensemble. So you have a sharp distribution at the corner of the simplex for confident inputs, for confident predictions, a sharp distribution at the center of the simplex when you have data uncertainty, and a flat distribution over the entire simplex when you have knowledge uncertainty. This is what we want. These are our desired set of behaviors, and they're basically the same behaviors as we would like our ensemble to have. Again, comparison to ensembles. In an ensemble, you have an implicit distribution over output distributions, and it's controlled by your prior p theta and the approximate inference scheme. Here, what we'll do is we'll construct an explicit distribution of output distributions, whose behavior is controlled by the loss function and the choice of training data. So basically, our underlying construct is still a conditional distribution of output distributions, but the way we get it and how we control its behavior has now changed. So again, just to drive home the point, we still have the same thing. We have our training data, we get a distribution over the simplex, we sample output distributions from it, and we get an ensemble of output distributions. And it operates in exactly the same way when you're confident, when you're data uncertain, and when you're diverse. Same thing here, so exactly the same thing as before. And for your measures of uncertainty, so this is what you had for your ensembles. This is your mutual information between y and theta, your model uncertainty, which decomposes into the total uncertainty given by the entropy of the expected minus the expected entropy of each model in the ensemble. And here we have the prior network uncertainty decomposition, and it's exactly the same. It's the mutual information between y and mu, and you get your total uncertainty by considering the entropy of the predicted posterior, and your expected data uncertainty will be the expected entropy of each model sampled from the distribution over the simplex. So they decompose in the same way, they operate in the same way. It's really basically trying to operate within the same construct. Now, the cool thing is that for a certain choices of prior network, you can do all this without any approximation. You can get all these measures of uncertainty in closed form cheaply, without any sampling or variational approximations, which is nice. So how do we construct one? So I've talked about this conceptual prior network. How do we actually build a prior network? Well, we're going to parameterize a Dirichlet distribution. Who knows what a Dirichlet distribution is? Hands up. Excellent. Yes, I like that much more. But yeah, it's basically a conjugate power of a categorical distributions, and we're going to have a neural network which predicts the concentration parameters alpha of a Dirichlet. And the reason we want a Dirichlet is because of some of the properties is to do with its conjugacy, and the other one is the fact that you can take all these expectations and integrals in closed form. So everything is analytically tractable, which is nice. So just a reminder, this is how a Dirichlet distribution is defined. This is a bunch of math. Basically, the important thing on this slide is that you have these parameters alpha, and the sum of all the alpha is alpha 0. It is called precision, and the higher alpha 0 is, the sharper your Dirichlet distribution is. And the expected posterior under Dirichlet will be given by the ratio of the alphas. So alpha 0 or alpha c over alpha 0 will be the probability, will be the expected predictive probability of class C. That's all sort of simple. Anyways, moving on. So as I've said before, prior networks are controlled by choice of loss and training data. Here, we set up a multitask loss function. We have our target in-domain training data, like CIFAR10, or maybe something else, maybe CIFAR100. And then we have to also have out-of-distribution training data. And how we get it, I'll say slightly later. And then the next thing is, what are our targets? So we want basically to specify this sharp distribution over the simplex at the correct corner for in-domain, and a flat distribution over the simplex, or a flat Dirichlet for out of domain. And now I'll basically talk about how we get that. So we want to construct a target Dirichlet distribution P mu given beta, where beta are also concentration parameters, for every input x in our training set. And ideally, we would like to have, for every x, the correct concentration parameters. But what we actually have is just the class label. We know the corner, but we don't know the concentration around the mode. So we lack a bit of data. So how do we deal with that? We're going to specify these concentration parameters manually by hand as a function of y. What we need is that beta reflects the confidence, so we need to set how sharp it is. We also need to make sure it's concentrated at the correct class, or the correct corner of the simplex, and the beta needs to be bigger than 0, because math. So, yes? Yes.
Why do we need it at all? Why do we need model uncertainty with the network?
Well, because we'd like to have a measure of uncertainty which is tractable, which is fast and computationally cheap, and doesn't involve lots of approximations.
Well, we already introduced such a measure.
Yes, we had Ensemble Approaches, but they have limitations. I'll do an experimental comparison a bit later, and I'll show you where both approaches are better and worse. But very right. Like prior networks are basically, they're a non-approximate. They're faster because it's just a single model versus ensemble approaches. But they have also their limitations, which I'll also mention later. Anyways, so now we're talking about how to train a prior network, and we need to specify these concentration parameters beta, and we're going to do that in the following way. Basically, beta C is now the concentration parameters for the target for class C, and they will be so beta is a vector, and it'll be beta plus 1 for the target class and 1 for everything else. So basically, if beta is large, it specifies a sharp Dirichlet at the correct corner of the simplex, and a beta 0 specifies a flat Dirichlet, where a flat Dirichlet is parameterized by concentration parameters 1. And this choice of concentration parameter is actually basically a posterior Dirichlet distribution, where you've seen the target class beta times, and you had a prior Dirichlet distribution which was flat. This is equivalent to basically having a Dirichlet posterior. And you'll see why, it's like, well, basically this is conceptually nice and also works out mathematically nice later. Right, so given this target Dirichlet distribution parameterized by the concentration parameters as I set them up before, we have two choices of loss functions. We can either consider the forward Keil divergence between our model P mu given x and theta and the target Dirichlet dir mu given beta c. And obviously we have to integrate, we're summing by the indicators of the correct class in the training data. Or we can consider the reverse Keil divergence. And as I've put them up here, they should conceptually, or it seems like they will, yield the same solution, because obviously this is 0 when both of them are the same. But it's not quite as simple as that. Now, just a reminder, Keil divergence is a standard measure of difference between two probability distributions. Here you have the forward Keil divergence, where we're taking the expectation of the difference of the log likelihoods of the target and approximating distribution. And we have reverse Keil divergence, which often comes up in variational inference, where we take the expectation with respect to the model of the difference of the log likelihoods of the model and the true distribution. Now, consider taking the expectation of the forward Keil divergence loss with respect to the training data. And our training data is x's and y's, right? So we take this expectation on our side, we take out the conditional true distribution over y given x, and that factors in here, and we suddenly see this mixture of Dirichlet there, this red bit. This mixture of Dirichlet, it's multimodal. And if you have a high degree of data uncertainty at a particular point, for example, consider a uniform distribution py given x, then you will have a multimodal mixture of Dirichlet with a mode at every corner. And this cannot typically be appropriately modeled using a single Dirichlet, which is unimodal. What happens is that because forward Keil divergence is 0 avoiding, it'll try to spread over each mode, and you'll get this. Basically, we want that behavior but on the left, but we actually get this behavior on the right, where the Dirichlet sort of inverts itself and it only has high probability density around the edge or the border of the simplex. And we don't want this behavior. This is a pathological behavior we'd like to avoid. So what do? Let's consider the expectation of the reverse Keil divergence. Same thing here, but now we're taking expectations here. You can open it up on line 2. You can open it up. You can put the expectation with respect to the conditional over y given x there, and it'll be basically the sum of logs, which will be the log of a product, and basically becomes a product. You can show some math such that it turns out we are actually minimizing the Keil divergence between the model and a single unimodal Dirichlet distribution whose concentration parameters are now averaged together. Now, I'm just going to tell you this math. I'm not going to show you this math. It's easy to do, and it really doesn't really, it's beside the point. You can show that this is the case, but you'll have an additional constant c, which disappears if you take an argmax with respect to the model parameters. So it's all fine. What this shows is that if you consider the reverse Keil divergence, you will be minimizing Keil divergences between two unimodal Dirichlet, so everything is fine. And you will get the desired behavior. And in fact, the target Dirichlet will now be sharp at the point on the simplex which corresponds to the correct estimate of data uncertainty in your prediction, as opposed to getting this pathological inverted behavior which you had before. That's nice. So we've established that reverse Keil is the way to go. It's the appropriate loss function, although I guess you can consider other ways of training them, but here we won't. For in-domain data, you have beta equals like 100 or 1,000 or some big value. For your out-of-domain, you have beta equals 0. But how do we get our out-of-domain training data? I sort of talked around the issue before. Well, basically, we need some out-of-distribution training data. There's 3 ways of getting it. You can either pick a different data set. So for example, if you're training on CIFAR 10, you can use CIFAR 100 as your out-of-domain data set. You can synthesize it using some kind of generative model, like a variational autoencoder or a GAN, or you can generate it using adversarial attacks. But that sort of is slightly different. And I won't really go into that. Basically, what do we want of our out-of-distribution training data? We want it to basically be close to the in-domain region, but not too close. So here you have the real in-domain training data in red. It's the 3 red clusters, and our out-of-domain training data is green. And if it's really far away, then some out-of-domain regions might be incorrectly considered in-domain. And if it's too tight and overlapping with the in-domain data, then some in-domain data might be considered out-of-domain. So we want this data to be really tight around the in-domain region. Crucially, we don't want to actually model the entire possible out-of-domain space, because that's vast and it's very sampling inefficient. We just want to get out-of-distribution training data which exists on the boundary of our in-domain region, where in-domain is defined by our data set. That's what we want. Furthermore, that out-of-domain data should lie also on the same manifold. What do I mean by that? Consider this nonlinear manifold. We have some images. This, like, for example, photorealistic natural images, they will lie on some underlying manifold. Those are our red points. And we want to collect out-of-distribution training data, which is also photorealistic images, which lie near our in-domain photorealistic images. We don't want to, like, for example, in this case, we don't want to consider adversarial attacks or noise or like maybe hand-drawn pictures because they will be off the manifold. And because in our, for example, in this application scenario, you're assuming that your out-of-domain will also be real. For example, you have a self-driving car and it's trained on images of cities. You want your out-of-domain to also be some kind of images of cities rather than cartoons, for example. This is, the other requirement. So here I've trained up a prior network on that toy data set there with the appropriately chosen tight out-of-domain data, but I used their forward KL, and I'm just illustrating what happens. Our total uncertainty is on the left over there, and is basically uniform where all the classes overlap. It's also uniform along the decision boundaries between two classes, and it's sort of only small where the classes are really sharp. Our data uncertainty is entirely uniform over the entire in-domain region, and our knowledge uncertainty is completely weird. So basically, we see that we don't get the correct behaviors of uncertainty here. It all goes horribly wrong if we use forward KL divergence. But if we use reverse KL divergence, it's all nice. You have basically total uncertainty is highest when you have, yes? Yes, it was trained on those circles. Right. So the total uncertainty is highest in the region of class overlap. It's a bit lower along the decision boundaries, and it's high again out of domain. Your data uncertainty captures that same structure of uncertainty in domain, and your knowledge uncertainty now is low and uniform in domain and high out of domain. These are the behaviors you want, and you see that given a good choice, and here obviously it's artificial toy data where I can get the perfect choice of data, it'll do well. It'll do exactly what we want. But obviously in a general situation, picking out of distribution training data is non-trivial and an open research task. So basically I've described prior networks, I've described ensemble approaches, and I think I might take the 5-minute break a little early and give you some pictures. You'll look a little tired. There's a little too much math in that last bit. So here we have the same data, it's overlapping classes, although they're colored in weird colors here. Basically, you have this same data set with 3 overlapping classes with a high degree of data uncertainty, and we have an ensemble of models, 10 models here, and I have a simplex that I'm basically plotting their output distributions. And here I visualized the actual uncertainty I get from my ensemble, and you can see that it's highest here. This is total uncertainty, it's highest here, and we see that basically our models are basically sort of the predictions of our models are sharp or concentrated at the center of the simplex. When I go along the decision boundaries, they're sort of sharp along a border, but they're sort of not perfect. If you go out here where it should be diverse, it's still sharp along that thing. Our estimates of data uncertainty are very similar, and knowledge uncertainty you see is sort of low here and high there, but because it's an approximation, there's something similar. If we consider, sorry, this is Monte Carlo dropout actually. Here's your actual ensemble. And it's a bit better. So yeah, this is your actual ensemble. It's a bit better, a bit sharper, a bit brighter out of domain, but it's still got weird regions. But again, this is because I trained a toy thing with really simple approximate inference schemes. If you use something more complex, you might get better estimates of uncertainty out of domain. It really depends on your approximate inference scheme, your prior is, you can get good behavior, I just didn't really get it here. With the prior network, I can sort of get almost perfect behavior, but assuming I have perfect choice of training data. And you see that basically our uncertainty, the total uncertainty is like this, bit red, kind of this demonic red, sharp, and the predictions on the simplex are tight and sharp at the center, and they sort of go to all the corners, but if I go out of domain, they're all over the simplex. So yeah, this is what we have. Cool. Is there any, so is everybody happy with that little illustration? Yes. Are there any other questions at this point before I go into assessment? Any other conceptual questions, slightly? Okay, cool. Then actually, I'm very quick. Right, so how do we assess uncertainty? How do we assess uncertainty? Typically, typically, you can, like, uncertainty is assessed using either the log likelihood of the test data or via calibration. And I think you might have discussed both in previous lectures here. I think there was a keynote talk on fairness and machine learning, and they might have talked about calibration. But I'll sort of summarize it very quickly here as well. Test log likelihood, it's super simple. You have your test data, and you're going to evaluate the sort of average negative, I need a minus sign there, forgot the minus sign. But yes, basically it's the negative log likelihood, the average negative log likelihood of the model, of the predicted posterior of your model on the test data. And if it's low, it's good. If it's high, that means your models think that the test data is low probability, which is bad. Now, calibration is slightly different. Calibration asks the question, do my confidences correspond to long-run accuracies? For example, if I'm predicting, let's say I have a bunch of predictions, their average confidence is like 0.75. Am I accurate only 75% of the time? And if I am, that means I'm calibrated. If I'm making a bunch of predictions and their confidence is 0.3, and I'm only accurate 30% of the time, that means we're also calibrated. If we have confidence is 0.99999, and I'm accurate 99.99999% of the time, I'm also calibrated. But if you have basically confidences which are like 0.9999, but your accuracy is actually like 56%, that means you're not calibrated. Do people get that? It's kind of simple. It's typically estimated with what's called expected calibration error, and you look at basically how calibrated different bins are. But anyways, these are nice statistics to have, and they're informative. But they're basically averages. They're average statistics. They're saying, how good is my uncertainty on average? It's like a kind of an accuracy measure for your uncertainty. And it's really only weakly related to some applications. And here's what I really want to stress: uncertainty. I feel this very strongly, is that uncertainty should be assessed in the context of an application. So you have some task which you want to use measures of uncertainty for, and you should look how good those measures of uncertainty are on a particular task. So, for example, you can consider threshold-based outlier detection, which is considered by Hendricks and Gimple. This is sort of baselines for outlier detection. And so you can consider misclassification detection, like can you detect when your model has made an error? That's one application, pretty useful. Can you detect an out-of-domain input? For example, if you have digits 0 to 9 and you're given a picture of a cat, can you detect that you're giving something the model doesn't understand? Or can you detect adversarial attacks? Adversarial attacks are pretty big these days. There are known weaknesses of machine learning methods, of neural net-based machine learning methods. Can we detect that we've been given an adversarial input? And basically, these are all very related. Like these tasks are related in the sense that you're going to assess it by having some amount of in-domain training data, in-domain test data, and some outlier data, and you're going to basically see how well you are, how good you can separate the two types of data using. And I'll talk about that more in detail later. But you can also consider using uncertainty for active learning. You can consider basically saying, look, I want to collect, I've trained my model, I've got some uncertainty estimates. I want to collect more data, which is useful, but I want to be efficient in that. I don't want to just collect tons and tons and tons of data. I only want to collect data which will make my model better. So here you actually also care about separation of source of uncertainty. Well, actually, you care about separation of source of uncertainty in the previous task as well. But in active learning, it's very clear. You want to collect data from regions where from regions you don't understand at all, and you don't want to collect data from regions where you have high data uncertainty, where you know that like you've seen this, you've seen data like this. There's no way to resolve this uncertainty. Let's just drop it and move on to something else. So active learning is one. You can also do uncertainty-driven exploration and reinforcement learning. Can you explore policies you don't know about? Maybe there's some space of policies you've seen, and they have these these attributes, but maybe I can try to explore previously unseen states or policies using my measure of uncertainty. If my measures of uncertainty are good for that. And there's many other tasks one can consider as well. So like this is by no means a definitive list of applications of uncertainty. These are just some examples. But in all these cases, but the important thing is that these are actual applications, and uncertainty, the quality of the uncertainty estimate should really be assessed on how good you do on each of those tasks, how beneficial the uncertainty is. Because after all, if you're just calibrated, but it's useful, your measures of uncertainty are useful for everything else, there's not much use to it. Anyways, so I will be talking about these two things, because I have lots of numbers for that. I also have numbers for adversarial attack detection, but I'm not going to show them because they're sort of preliminary, and I don't really trust them myself right now. And we're going to talk about the first two. So threshold-based outlier detection. You have some indicators, so you have some measure of uncertainty h of x. If it's bigger than some threshold t, you are uncertain. And it's an outlier. If you are less than if your uncertainty is less than some threshold t, you're normal. You're not an outlier. It's all good. And you can evaluate the performance at a range of thresholds because you're picking thresholds arbitrarily. You want to pick a threshold, and you can sweep through all the different thresholds and see how well you can separate these out. So you can either plot a precision recall curve, you can plot precision over against recall and measure the area under precision recall curve, or you can plot your true positives versus your false positives, I think. Maybe I got that wrong. Anyways, but standard ROC curves are pretty standard, and again, you can plot that curve and measure the area under that curve, and that'll be a summary statistic. It won't be a performance, because performance is only at a particular threshold, but it'll be a summary statistic of the achievable performance points on these tasks. Now, and area under precision recall curve is good for misbalanced data sets. For example, misclassification detection, because you care about the precision and stuff. Basically, if your outliers and inliers are misbalanced, like let's say you have a very accurate classifier, you have, let's say, 3% error rate, you have 3% of your test set is outliers, and 97% is inliers, you have a misbalanced set. Good performance in an area under precision recall curve is obviously 100%, 100. Random performance, however, will be the error rate of your classifier. It changes. It is not obvious that. This is a bit of a weird metric. It makes comparing systems a bit difficult, but this is the case. For an area under an ROC curve, it's a bit simpler. It's good for balanced data sets where we have equal amounts of positive and negative examples, outliers and inliers. Good performance is 100, random performance is 50. If you have negative performance, you will get good performance by switching the class labels. Basically, if you have like a performance of like 3, that means you can actually get a performance of 97 by flipping the positive and negative labels. So it means it's good, it's just, for example, it's all switched. Anyways, so this is that. It's like I really should have had pictures here, but I didn't quite have time to make that. Right, so our experiments, where I'll be comparing prior networks versus ensembles, we have prior network compared to deep ensembles, and the reason I picked deep ensembles is because it's really cheap and easy to make, given enough compute. Our in-domain training data is CIFAR10, so it's a 10-class image classification problem. Our out-of-domain training data for a prior network is CIFAR100, which has non-overlapping labels with CIFAR10. And our out-of-domain test data for out-of-domain input detection will be SVHN images, LSIN images, and tiny ImageNet images. And tiny ImageNet looks a lot like CIFAR10 and CIFAR100, so it's actually pretty, like I wouldn't be able to tell apart tiny ImageNet from CIFAR10 or CIFAR100 unless I actually knew the class labels. So it's a non-trivial task. I've built a bunch of models, and I'm sort of comparing a standard DNN, a prior network trained with forward KL to really drive home the point of that it's an incorrect loss function, and a prior network trained with reverse KL, and our ensemble performance. And basically, DNNs perform about as well as prior networks. I think the extra training data for the prior network, the out-of-domain training data works a bit like a regularizer, so you get a bit of better performance in classification. And we've been able to build all models on CIFAR10. In this case, I've also built models on CIFAR100 and tiny ImageNet just to illustrate that we can. And we couldn't build models on CIFAR100 and tiny ImageNet on using forward KL. We just wouldn't train. It went all bad. So yeah, this just shows that reverse KL is also important. But clearly, as you can see, the ensembles get much better classification error rates than prior networks. Prior networks, again, so this is a limitation of a prior network. Prior networks are still based on a single estimate of a set of model parameters rather than using an ensemble. And ensembles, because you're integrating out over different models or different model parameters, they give you better classification error rates. This is a benefit of ensemble approaches. Here, I've applied ensembles and prior network training using reverse KL to the task of misclassification detection. And here I'm using measures of total uncertainty and knowledge uncertainty for this task. Here, I'm assessing performance using area under precision recall curve. My random performance for all the models will be the error percentage, the either 6.2% or 7.5% is the random thing. And the fact that my actual area under the precision recall curve is like 48 or 40.5 in the best cases shows that I am actually doing something meaningful. I can detect a certain amount of outliers, or I can detect a certain amount of misclassified results. But it's not perfect because it's not 100. Now, you'll notice that here the ensemble again outperforms the prior network. And that's because ensembles, so like if you sort of remember at the beginning, I talked about knowledge uncertainty in a very particular sense that is due to distributional mismatch. You've got inputs from different data sets. But knowledge uncertainty also, epistemic uncertainty, of which knowledge uncertainty is part, and which is captured by the model uncertainty of an ensemble, also captures uncertainty due to data sparsity in domain. And this is where the benefit of ensemble comes into play. Ensembles do better on misclassification detection than prior networks, because prior networks see only the in-domain training data for the in-domain, and the out-of-domain training data is out-of-domain. So yeah, interesting. So here ensembles are better. Also, what is better is measures of total uncertainty are better at this task than measures of knowledge uncertainty. Here, if you use the entropy of the predicted posterior or the confidence of your predicted of the max class, that is a better measure of uncertainty to use than knowledge uncertainty, than mutual information, or this difference thing. And the reason for this is kind of obvious. You don't care why you've made an error, you just care that you've made an error. You don't care whether this is far away from the training data or on a decision boundary, you care that you've made an error. So, makes sort of sense. Any questions at this point? Cool. Here, we're talking about now out of distribution input detection. Here, we're only talking about models trained on CIFAR10, and we're measuring performance using area and an ROC curve. Here, we have balanced in-domain test sets and out-of-domain test sets. So our in-domain test set is CIFAR10 test set, and our out-of-domain test sets are SVHN, Elson, and Tiny ImageNet, which is scaled down to 32 by 32. And we're comparing, again, ensembles and prior networks. And in this case, prior networks consistently outperform ensembles because they've been told what is, basically, you've used training data to build in knowledge about the limitations of knowledge, to sort of learn that boundary of the in-domain region. And so now we have prior networks outperforming ensembles on this task. And on this task, measures of knowledge uncertainty are better than measures of total uncertainty, because you can have high uncertainty, but it might be because you're on some, the input is on some region where multiple classes overlap, but that's still in domain. It's not out of domain. And by separating out knowledge and model uncertainty, we can do better, on prior networks at least. For some reason, the ensemble knowledge uncertainty wasn't as good. But again, it's really hard to guarantee the behavior of an ensemble, especially one which is trained using random initializations, because you just randomly initialize a bunch of parameters and you train to some point and you hope it has the behavior you want, but might not necessarily. So this is an example where prior networks do better than ensembles. Anyways, so that brings us to sort of the end of the main bit, and we get to really weird territory here, which is some of the stuff we're working on now. It's called Ensemble Distillation. Now, as you just saw, ensembles gave us better classification performance, and ensembles gave us better misclassification detection performance, while prior networks did better at out-of-domain input detection. Now, here's a question. Can we combine the benefits of prior networks and ensembles? I mean, also ensembles were 10 times more computationally complex because I was running 10 models. So it took me 10 times longer to do everything, while prior network was just one model. So can we combine the benefits of ensembles and prior networks and get the best of both worlds in some sense? And the answer is kind of, or it seems so far. So there's been work done on ensemble distillation, and you basically, ensemble distillation is when you have a bunch of models and you try to distill the predictions of a bunch of models into a single model. And this is, so when you have one, distilling one model into a different smaller model was work done by Hinton et al. It's called dark knowledge, or dark knowledge or something like that. And then Kartikara and I think Welling did work on Bayesian dark knowledge, where you distill an ensemble of models into a single model. So ensembles are computationally complex, and stuff, but they have nice benefits. What we can do is we can distill an ensemble to a single model. So we have a bunch of predictions, and we want to capture that bunch of predictions using a single model. And what people typically do, like the really simple thing here, is that you will minimize the scale divergence of your model to the predicted posterior of the ensemble. You'll basically average together the predictions of the ensemble, and you'll minimize the scale divergence. Really simple so far. And this is known to give us computational gains. It improves the predictive performance of a single model. And it's also been known to give us improvements in robustness to adversarial attacks. Now, I don't actually consider that here, but that is a known use of distillation. However, ensemble distillation only captures the mean of an ensemble. We lose, the diversity of the ensemble around the mean is lost. And we can no longer separate out the measures of uncertainty. We can no longer get total uncertainty and knowledge uncertainty. We can only get total uncertainty. Sorry, we can no longer get knowledge and data uncertainty. We can only get total uncertainty. So our solution, or our proposed solution, is something called ensemble distribution distillation. And this is some like this is right now it's just an archive paper. But anyways, the idea is basically we have our ensemble, we have our predictions of the ensemble. There are a bunch of points on a simplex for a particular input x. I assume you're all happy with that by now. And we're going to basically try to distill that into a single prior network, because prior networks emulate ensembles. They are also distributions over distributions. Both are, so can we model an ensemble directly using a prior network? And our goal here is basically when you distill only the mean of an ensemble, you lose information about the diversity. Here, our goal is to maximally extract all possible information from the predictions of an ensemble. So both the mean to get performance improvements in classification performance, to extract the mean to get all the improvements in misclassification detection as well, but also to capture the diversity of the ensemble. And hopefully that will yield other benefits, which we haven't discovered yet, but hopefully they will. So how do we do ensemble distribution distillation? We have a prior network again with parameters of Dirichlet by predicting the concentration parameters. Nothing different. It's all the same. And our training data here is the predictions of an ensemble at every point. So for every x, we have the categorical distributions mu predicted by an ensemble. And this will be our empirical distribution p hat, mu, and x. And what we're going to do is really simple. We're going to maximize the likelihood of those predictions by the prior network. This is super simple, but kind of cool. Does everybody get this? Is there any questions? Cool. So an illustration here is basically we have this toy data set. It's a bit more complex than the previous toy data set. We have 3 classes. They're in a spiral. We just thought we'd go for something which is really nonlinear in this case, so it's a bit harder. Okay, so now basically here are the measures of uncertainty derived from an ensemble on top and a ensemble distribution distilled prior network on the bottom. And basically it's the same spiral data set, we've just zoomed out a lot. On the top, on the right, in the right column, in the left column, you have estimates of data uncertainty. That's the entropy of the predicted posterior of either the prior network or the ensemble. And here we have an ensemble of 100 models. So it's 100 times more expensive than a prior network. In the middle, we have the data uncertainty, so it only captures that sort of uncertainty due to class overlap around the spiral. So there's only ever overlap between 2 classes because only 2 classes are near each other in a spiral. And on the last one, we have the knowledge uncertainty, and it's dark. So dark, in this devil red diagram, dark is low uncertainty and bright is high uncertainty. So basically, knowledge uncertainty with the ensemble is dark in the middle, which means we know exactly what's going on. All the models in the ensemble agree at the center. They disagree. They also agree, and they disagree around. This is exactly what we want. Is everybody happy with this? And on the bottom, we can see that our prior network, trained using maximum likelihood on the predictions of this ensemble, has fully captured this, more or less. It's quite close. Now we've captured the in-domain uncertainty, we've captured the knowledge uncertainty, we basically replicated the measures of uncertainty derived from diversity of the ensemble, but now we just use a single model for it. So we're now 100 times faster, because I try and train an ensemble of 100 models here. So it's nice. It's nice that we can do this, but this is a simple task. So we expected to be able to do this. Yes? Yes. So this is really up close, and here we've zoomed out. There's just for some reason along some lines the uncertainty is much higher. So basically, it's a heat map of uncertainty. These diagrams are a heat map of uncertainty. In regions which are very bright, the uncertainty is very high, and regions which are very dark, the uncertainty is very low. And what these diagrams show is that uncertainty is high along the decision boundaries in a spiral at the center, and uncertainty is also high everywhere around. That's our measure of knowledge uncertainty. So total uncertainty is the uncertainty along the decision boundaries in the center, and the outer domain uncertainty around that. And when we decompose the two using an ensemble, we get the uncertainty only around the decision boundaries at the center, and the uncertainty everywhere out of domain around on the right. And here on the bottom, we show that the prior network trained using ensemble, the ensemble distribution distilled prior network captures the same behavior, or sort of captures the same behavior overall. That's nice. But like we expect that we can do this on this toy data set. Can we actually do this on something a bit more serious? So here we've done ensemble distribution distillation and compared it to so here we have 4 types of models. We have individual models, so these are the mean predictions of a bunch of neural nets. We have an ensemble. We have an ensemble of neural nets, and we're looking at the classification performance of the predictive posterior of the ensemble. Then we have ensemble distillation, where we've minimized the KL divergence between the model and the predictive posterior of the ensemble. And finally, on the right, we have, in the last column on the right, we have the classification error rates of an ensemble distribution distilled model. And we can see here that our models now have much higher classification performance. Lower classification error rate, higher classification performance. We're now closer to the ensemble than the individual models in all cases. About halfway there. That's nice. So basically, we've gained performance. So we're closer to the classification performance of an ensemble, but for much less computational cost. That's nice. Here we're looking at misclassification detection. Basically, here we're looking at models trained on CIFAR10, CIFAR100, and Tiny ImageNet. And again, we have the individual model, the ensemble distilled model, the ensemble distribution distilled model, and the ensemble itself. And here, the important thing to look at, because we're looking at area under PR curve, is the difference between the AUPR and the error rate. And we can see that for CIFAR10, we're actually slightly outperforming the ensemble using all models for some reason. That's nice. On CIFAR100, our ensemble still does better, but both our ensemble distilled and ensemble distribution distilled models have lower error rates and slightly, well, about the same AUPRs, but the difference has increased. I really should have plotted the difference here on these tables. Anyways, but the point is we've gained in misclassification detection performance. The best is still the ensemble. And same story for Tiny ImageNet. But I think the gains there are much bigger because the models really overfit on Tiny ImageNet. So basically we've really dropped our error rate to 37.3, and our AUPR has only dropped by like 1, which means that the difference between AUPR and the error rate has increased. So we've improved our misclassification detection performance using ensemble distribution distillation. So that's another win. Finally, we are looking at out-of-distribution input detection using all of our models. And here we consider 2 out-of-distribution test datasets, ELSON and Tiny ImageNet, and we're not looking at models trained on Tiny ImageNet. We're only looking at models trained on CIFAR10 and CIFAR100. And there's a couple like interesting points here. So there's a lot of stuff in this table. Firstly, firstly, both in the individual models and the ensemble distilled models are much worse than either the ensemble or the ensemble distribution distilled model using any measure of uncertainty and any so basically they're much worse. Ensemble distribution distillation and the ensemble themselves yield the best performance on this task using area under an ROC curve. That's nice. So basically, so even using total uncertainty, and like a reminder, total uncertainty is derived only from the predictive posterior. So there seems to be something which ensemble distribution, some information, some underlying information, which ensemble distribution distillation conveys to the model through its diversity, which improves the behavior of even the predictive posterior of of the ensemble distribution distilled model. That's nice. So there's something that ensemble distribution distillation gives us, which normal ensemble distillation doesn't give us. So clearly that information is useful. Secondly, we can also decompose the measures of uncertainty, and we do better using knowledge uncertainty than we do using total uncertainty. That's also nice. It basically says that the decomposability of uncertainty and separating out the source of uncertainty is still important for this task, which makes sense. Interestingly, sometimes the prior network, the ensemble distribution distilled prior network outperforms the ensemble itself. And I think the reason for this is that the behavior of an ensemble is not always distributed like a Dirichlet. Our ensemble, the distribution of the predictions of an ensemble on a simplex might be distributed in some very different way, which is badly captured by a Dirichlet. But overall, it ends up capturing a higher degree of uncertainty there. And so there might be some smoothing process going on. Remember, forward Kell divergence, and here we're going back. So maximum likelihood is equivalent to forward Kell divergence between the model and the underlying distribution. Here, forward Kell divergence does yield good things because we actually have a distribution over predictions. And it seems that forward Kell divergence, by being zero avoiding, sort of increases its estimates of uncertainty when the ensemble gives you non-Dirichlet distributed predictions. But this is my sort of assumption. So basically, this is nice. So ensemble distribution distillation can outperform the original ensemble on this task. The information we extract from the ensemble is useful. We get computational gains. We get improvements in misclassification detection. We get improvements in out-of-distribution input detection at reduced cost, and it's all tractable, and it's all nice. So, but this is still a work in progress. I still the models I used, the architecture of the models I used was VGG, so we can expect to push everything up by transferring to something like a ResNet or a wide ResNet. We still haven't evaluated on adversarial attacks. It'd be interesting to see whether ensemble distribution distillation gives us better robustness to adversarial attacks than ensemble distillation due to the extra information conveyed. So this is the stuff we're working on now, and we'll see who's interested. Anyways, this really actually brings me to the end of my talk. I went really fast, but it gives us lots of time for questions if there are any. The takeaway points are that there's multiple sources of uncertainty. Data uncertainty is uncertainty due to class overlap. Knowledge uncertainty is uncertainty due to out-of-distribution inputs which come from a distribution different to the one you're training on. And data uncertainty is a known unknown. We understand that data when we know that we are uncertain here. And then knowledge uncertainty is an unknown unknown, is harder to model, requires ensemble approaches or prior networks it requires having a mechanism to build in knowledge about the lack of knowledge. This source of uncertainty. We have ensembles. Ensembles are implicit and not in the same sense as yesterday. Implicit distributions over output distributions. But they are samples from distributions over output, they are samples from a distribution over output distributions. Now ensembles, Bayesian ensembles in particular, are a theoretically motivated way to separate out the source of uncertainty. They're nice. Their behavior is controlled via prior and also the choice of approximate inference scheme, and is in general sort of difficult to do that. It is non-trivial. It is still a very open and a very interesting area of research. And they're also slightly more computationally complex than single models. Then we have prior networks, which is what I work on. It's an explicit distribution of output distributions. We have a single model which on the output is a conditional distribution over output distributions, and we chose to parameterize a Dirichlet distribution, but we could have gone for other distributions in principle. We're not really married to the Dirichlet. And prior networks emulate ensembles. They have the same decomposition of uncertainty. They emulate the same behavior, but through a different mechanism. They do it via the choice of training data and the loss function. And right, so uncertainty assessment. So as I've said, the important thing about uncertainty assessment is that we want to apply uncertainty to end tasks or end applications. It's nice to look at calibration. It's nice to look at negative log likelihood. They're informative things. But I strongly believe that what you want to do is you want to apply your uncertainty to some end task, see whether your uncertainty does good. And as we saw before, ensembles apparently did better on classification, but ensembles did also better on misclassification detection. And prior networks did better on out-of-domain input detection. And different measures of uncertainty give us better performance on the two different tasks. So we also care about separating out measures of uncertainty. And this is nice to know, because things like calibration and things like negative log likelihood only look at the predicted posterior rather than behaviors of the distribution over distribution itself. Finally, well, I'm looking at, like, I showed off some of the stuff I'm working on now. It's called Ensemble Distillation. It's basically the idea is you're going to distill an ensemble into a prior network. It's like a combination of prior networks with ensembles, and the point is to combine the benefits of both. Basically, you get the classification performance, or closer to the classification performance of an ensemble, as well as the misclassification detection performance, and hopefully you'll also be able to do better out-of-domain input detection like you would with a standard prior network. That's nice. So anyways, thank you. If there's any questions, I will gladly take them now.
Thank you. What is about like regression tasks?
Right. So I didn't talk about the regression tasks because, sorry. So it's a good question. The story for regression tasks is exactly the same, but we're now working with distributions over continuous values, and they're much harder to visualize. So I decided not to put them in this talk because I was really going for building visual intuition. But the idea is the same. You have a, you can have like Ensemble Approaches will have an ensemble of models which each parameterize a distribution over output distributions, and you can consider things like mutual information, entropy of the differential entropy of the expected differential entropy, their differences, and so on and so forth. So exactly the same thing. For prior networks, the other thing I'm working on now is prior networks for regression, and for regression prior networks, you would parameterize something like a normal inverse Wishart distribution over output distribution, over normal distributions.
Don't you need to use like Dirichlet processes?
No, sorry. Dirichlet processes is something slightly different. Dirichlet processes are for, I think, dynamically picking the number of components of your Dirichlet. It's slightly different. For regression tasks, where you're trying to, so if your training data is a bunch of x's and continuous targets y, you can try to specify an output distribution over y, and that will be a density network. A neural network which basically gives us p of y given x, where the p of y is over continuous y, it will be called a density network, and mixtures of density networks are something which was explored in the 90s by Chris Bishop, who's now at Microsoft Research. And they're good for, and basically mixture density networks are great for capturing the data uncertainty in your y's. But your data uncertainty for regression tasks will be due to various forms of noise, whether it's data-dependent or data-independent noise. So you can, for example, pick a mixture of normal distributions over y's condition on x. That'll be your model. That'll be your predictive distribution. And then to go Bayesian or to go ensemble, you would make an ensemble of mixture density networks, for example, where each model in the ensemble predicts a distribution over targets y. So you'll have, again, a distribution over distributions over continuous targets. So it's all the same. The ideas are the same for regression as for classification. But unfortunately, because you're now dealing with continuous distributions, not everything ends up being analytically tractable, even for prior networks. So, yeah. Any other questions? Yes? Yeah, left. Guy on the left. Wait, whatever. You first.
Thanks for the talk. On the slide 64, can you again say what's the ensemble, the last column, and why there is no variance available?
Is the slide 64 the same one as I have here? Because I have all the pauses here. Yeah, actually it is. Cool. Go here. A few more, almost there. Yes. Cool. Yes?
Sorry, 60. Okay, it's different from the version that I've got here. So then 65.
65. Yes,
yes.
Okay.
The last column, again, what it is and why the variance is not available. Like.
Oh, right, because we have, so basically what I did was I trained 10 models, 10 DNN models using maximum likelihood, standard models, and the average performance of those models is what we have in the left column, and the performance of the average of those models is the ensemble. So basically I constructed a deep ensemble. I initialized 10 neural nets, trained them separately. I've constructed an explicit ensemble of models, and the variances are not available because I basically had 10 models. I combined their predictions into a single prediction, and that's my prediction of the ensemble.
But then how could we make sure that it's statistically significant?
Well, well, what you probably want is you'd make 10 ensembles, and you would measure the variance across the 10 ensembles. But I didn't have enough compute time to do that. So, yeah.
Thanks.
I mean, in practice, you would do that. I just didn't. But like at some point later, so just to answer the question, for the Ensemble distribution distillation results, I did train 100 models, and the difference in performance between 100 models and 10 models was not very big at all. Like there's a much bigger gap between 5 and 10 than between 10 and 100. Yes, Guy. So there's a question there on the left.
Hi. First of all, thank you for a great talk. I have actually 2 questions.
Sure.
The first one, you had that slide with these plots distilling the predictive uncertainty from the ensemble to the ensemble distill network.
Was it this one?
No, it was 2 rows and 3 columns.
This.
Yes,
Okay, yes.
in the middle column.
Yeah.
Do you have an explanation why do you overestimate somehow the data uncertainty?
I think because, like, sorry, so you're basically asking why it's a little why it's a little more purple.
Yes,
than
because
right,
the
okay,
other
okay.
2 plots look like a perfect distillation, and in the middle, they're somehow overestimating this uncertainty.
So you mean sort of around here? So if we look here, you're looking here, like around the spiral. Yeah, I'm not sure. I mean, it is a maximum likelihood estimate. In the end, we've lost our model uncertainty because we've distilled a bunch of models into a single model. It's not perfect. You know, also you're basically distilling on the training data. So you've used some data to train 100 models in this case, and then you're using the predictions of the models on the training data to train your ensemble distribution distilled model. And obviously, you'll be much sharper on the training data, which is all in domain, than around. So there may be some lack of ability to generalize a low data uncertainty fully in these regions. I mean, like, it's something to do with the estimation, and I'm not sure. Like, if you use more organization, maybe it'll do better. I'm not quite sure.
Okay, thank you. My second question is about prior networks.
Yeah, sure.
You showed you need this out of distribution data, and you showed this plot with the manifold, and this doesn't seem trivial in practice to me, because how do I get this manifold? Because, or to say in other words, if I have an analytical formulation for this manifold, I could imagine to.
Oh, sorry. Like, the manifold was only conceptual. It was a conceptual idea. I don't actually mean you need to estimate a manifold, right? I was trying to conceptually illustrate the idea that, like, you have, like, for example, if you're training your model on photorealistic images, for example, on, like, you're training your self-driving car on images of streets and cities and people and so on, your out-of-distribution data should be also images of streets and people and so on in entirely different situations, like, you know, maybe with snow or with other rain or whatever, right? You don't want to use, like, hand-drawn pictures as out-of-distribution training data for a self-driving car. That's what I mean by being on the same manifold. It was just a conceptual idea, right? Now, off manifold, and some people might argue with me here, I would say that adversarial attacks go off manifold. And the stronger the adversarial attack, the stronger the perturbation of the adversarial attack, the more off manifold you go. And this is the case if you want to use prior networks to detect adversarial attacks, you have to train them on maybe some form of adversarial attack, such that it also gives you high uncertainty off manifold, not just on manifold. But when you're looking at, like, for example, uncertainty in, like, real applications, like for self-driving cars or maybe some image detector or something like that, or some medical application, you want your out-of-distribution training data to also be from somewhere near the same domain. So rather than using weird illustrations or hand-drawn pictures or you know, something like that. Now, if you're using a generative model, for example, like, say, a GAN, you want your GAN, you know, to be giving you something sensible for your out-of-distribution training data, rather than completely weird noise stuff. That's also what I mean by being on manifold. But yeah, like, I'm not using this in a strict, like, some differential geometric meaning of manifold in this case. This is more conceptual.
Thank you.
Any other questions? Okay. Cool, thank you.